5, we're now going to start factoring polynomials using, start with this review portion here. Consider the polynomial x squared minus x minus 6. The function can be expressed in factored form as f of x equals x plus 2 times x minus 3. So we're going to fill in the blanks. The graph of f of x equals x squared minus x minus 6 as x-intercepts at negative 2 and 3. The function x squared minus x minus 6 has zeros at negative 2 and 3. The equation x squared minus x minus 6 equals 0 has roots at negative 2 and 3. Fill in the blanks. The function with equation y equals f of x. So the zeros of the function, the x-intercept of the graph of the function, and the roots or solutions of the equation y equals 0 are all the same vectors. So not only does this process let us factor things, it actually answers all 3 of these questions for us. It's already been factored for us, so we know the zeros are negative 8 and 3. What do you notice about the constant term of the polynomial and the zeros of the polynomial? The zeros are factors of the constant term. The factors of the polynomial p of x equals x cubed minus 2x minus x plus 2 are x minus 2, x minus 1, and x plus 2. State the zeros. They are 2, 1, and negative 1. And what do we notice? Well, 2, 1, and negative 1 are all factors of the constant term. Illustrations of the integral zero theorem. You don't really need to know that term, but which states that the zeros of an integral polynomial function with a leading coefficient of 1 must be factors of the constant term. So consider p of x equals x cubed minus 7x minus 6. The integral zero theorem tells us that zeros of p of x must be factors of negative 6, and so must come from the list plus minus 1, plus minus 2, plus minus 3, plus minus 6. Those are all the potential zeros. Consider the polynomial p of x equals x cubed minus 7x minus 6. So list the potential zeros. So we're going to list all the factors of negative 6. So it is plus minus 1, plus minus 2, plus minus 3, plus minus 6. So what are the potential factors? Well, then the potential factors are x minus 1, x plus 1, x minus 2, x plus 2, x minus 3, x plus 3, x minus 6, x plus 6. So we know our factors come somehow from this list. So students were asked to identify when the actual factors of the polynomial. Luke used the factor theorem, Nicole used synthetic division. So we'll look at Luke's work here first. He found x minus 1. He substituted the 0 of that in, which is 1, and he got negative 12. So that tells us it's not a factor because we need it to equal 0. So he moved on to his next factor, trying x plus 1. So he substituted in the 0 of that, which is negative 1. Found the remainder to be 0, so could tell us for sure it was a factor. He then used synthetic division. You could, of course, also use long division to figure out what is left after dividing. Nicole tried x minus 1 as a factor first using division, got a remainder of 12. That told her that is not a factor. Then she tried dividing by x plus 1, got a remainder of 0, found out it was a factor. Complete the factoring. Well, so far we know that x cubed minus 7x minus 6 is equal to x plus 1 times x squared minus x minus 6. So to complete the factoring, we need to factor this quadratic if possible. Sometimes it won't be possible, and then you'd stop at this stage. sometimes you could use the quadratic formula like we'll do in a couple examples here to help you finish it off. But this one's easy to factor. So multiply to -6, add to -1 would be x minus 3, x plus 2. So now we have fully factored. So some people like to do division all the way around. Other people like to do factor theorem. I prefer the factor theorem simply because the calculators we have, we can kind of leave this whole thing punched in and we can go back and edit it and just change the input numbers. And then it's pretty quick to run through a number of values. Synthetic division would get pretty tiring if your first factor wasn't until x minus 6. Okay, so now we're considering the function x to the 4 plus 2x cubed minus 7x squared minus 8x plus 12. So all the potential zeros are all the factors of 12. Quite a long list. More often than not, you'll have factors from the first few values. So we actually see that if we substitute in 1, we get it equal to 0. So that tells us our first factor is x minus 1 is a factor. So now that we've found one factor, we're going to use division, whether you want to use synthetic or not, or long division's up to you. I'm going to use synthetic just because they don't really give us room in the book here to do long division. So I put my 1 here, my coefficients 1, 2, -7, -8, and 12. Bring down the 1. 1 times 1 is 1, adding gives us 3. 1 times 3 is 3, adding gives us -4. Oops, and I made a mistake here somewhere. This should be 12. I subtracted there instead of added. Should be -12. 1 times -12 is -12, adding gives us 0. It's always a good way to check your division. If you get a remainder here that wasn't 0, but you knew p at 1 was 0, then we know there was a mistake in our division. So right now we know that p of x is equal to x minus 1 times x cubed plus 3x squared minus 4x minus 12. So now we need to repeat the process with x cubed plus 3x squared minus 4x minus 12. And if we do this, we find that p of 2 equals 0. So now if we put 2 in for here, we find that p of 2 equals 0. It would also make the original equal 0. So this tells us we have a factor of x minus 2. So we're going to do division again with our cubic this time. So now we have p of x equals x minus 1, which was our first factor we found, x minus 2, which is the second factor, and then x squared plus 5x plus 6. So again, now we have a quadratic. We want to factor that. And this becomes x minus 1, x minus 2, x plus 3. And x plus 2. It really doesn't matter which order you do this in. If you find that your first factor would be x minus 2 and you divide it here, it all works out in the end. So there's nothing magical about starting with this 1. You could have found any of those zeros and it would have worked out. So C says state the zeros. Well, now I can just go through each factor, list the value of x that makes it 0. State the roots of the equation when that polynomial equals 0. Well, it's the exact same number. I guess we should really put x equals there. Okay, 3 is a slightly different application of this. So consider the polynomial function p of x equals x cubed minus 3x squared minus 3x plus 1. Find the zeros of p of x to the nearest 100 using a graphing calculator. So if you were to graph this and find all the zeros, you would get -1.00, 0.27, and 3.73. So these aren't exact values here, which is kind of a problem if we want to factor this. And it turns out that if these cannot be written as exact values, we don't have factors, a way to factor it. We could use the quadratic formula to find the zeros, which is what we're going to do. So use the integral zero in A and synthetic division to determine the exact value of the zeros. So we know that 1, 0 is negative 1. So we can use division to divide that out. So we know we could write this in factored form as x plus 1 times x squared minus 4x plus 1. Well, if we look at this factor, x squared minus 4x plus 1, we're looking for two numbers that multiply to 1 and add to negative 4. Well, we cannot find those numbers. So if this question said factor the polynomial, we would simply leave it like this and we'd be done. But it asked us to find the exact values of the zeros. Well, how do we find an exact value of a zero of a quadratic that we can't factor? We use the we use the quadratic formula. So we're going to substitute in. Our b value is negative 4. So negative 4 squared minus 4 times 1 times 1. A and c are both 1 over 2 times 1. So simplifying this, we get 4 plus or minus root 12 over 2. Now you do need to remember how to simplify these radicals. So the highest perfect square that goes into 12 is 4. So we can rewrite it like that. Then we can take the square root of 4 and put it out front. And lastly, to simplify this, we can divide each term up top by the 2. So this is equal to 2 plus or minus root 3. So those are the zeros. So all of the zeros, we shouldn't forget the zero of negative 1. Oh, that's not how you spell 0. So negative 1, 2 plus root 3, and 2 minus root 3 are the zeros.